Every time you use your phone, your computer, or pretty much any piece of modern tech, you're interacting with a world that speaks a completely different language. It's a language made of numbers, but probably not the kind you're used to. Today, we're going to decode that secret language. It really all comes down to this one simple question. You and I see the number 45, but a computer just sees a bunch of on and off switches, a series of zeros and ones. So how in the world does it get from our number to its language? That's the exact puzzle we're going to solve together right now. To answer that question, first we need to get our heads around the fact that we're dealing with different languages, or, to be more accurate, different number systems. Think of it like this. You have to learn the basic grammar of a language before you can start translating sentences, right? It's the same idea here. And here's the fundamental difference right off the bat. Our system, which is called decimal, is a base 10 system. It means we have 10 different digits to play with, 0 all the way through 9. Computers, on the other hand, they work in binary, which is a base 2 system. They only have 2 digits, 0 and 1. That's it. And believe it or not, everything a computer does is built on that simple yet incredibly powerful foundation. So let's go ahead and meet the key players in our translation guide. We're going to be looking at 3 main systems: our familiar decimal system, the computer's native language, binary, and another one called hexadecimal, which is a really useful kind of shorthand. Okay, this table lays it all out for us perfectly. You can see decimal is base 10 with its 10 characters. Binary is base 2 with just 2. But then you've got hexadecimal, a base 16 system. And notice this, it uses our regular numbers, 0 through 9, but then it adds the letters A through F. Now that might seem a little strange at first, but it's actually a super efficient way for developers to write out long, clunky binary numbers. We'll see exactly how in just a minute. All right, let's start with the most important translation of all. How do we turn a computer's binary code into a number that actually makes sense to us? This is where we crack our first code. Remember our big question from the beginning about the number 45? Well, this is it. This is what a computer actually sees. 101101. Right now, it might just look like a random jumble of digits, but I promise we're about to translate it step by step. So the very first step is to understand something called place value. In our regular decimal system, we have the ones place, the tens place, the hundreds place, and so on, right? Well, binary has the exact same idea, but instead of powers of 10, it uses powers of 2. So starting from the right, you have the ones place, then the twos place, the fours, the eights, and it just keeps doubling every single time. Step 2 is actually the easy part. The ones in that binary number just mean that position is on, and the zeros mean it's off. So all we have to do is add up the place values for every single position that has a 1. Looking at our number, we care about the values 32, 8, 4, and 1. And when we add them all up, 32 plus 8 plus 4 plus 1, we get 45. And there it is. Boom, mystery solved. That binary number, 101101, is just the computer's way of saying 45. Okay, let's dive into this with another example, just to make sure it really sticks. What happens if all the switches are flipped to on? Let's figure out the decimal value for the absolute largest number you can possibly make with 8 binary digits. That's 8 ones all in a row. We use the exact same method. We just add up every single place value, from 1 all the way up to 128. The grand total is 255. Now, this is actually a famous number in the world of computing because those 8 binary digits together make up what's called a byte. And 255 is the maximum value that a single byte can possibly store. Awesome! We can now read the computer's mind. But what about the other way around? Let's take a look at how we can translate our numbers into a language that the computer and other programmers can understand really efficiently. This table gives us a couple of new challenges. We can see how a number like 59 becomes a pretty long string of ones and zeros in binary. But notice something a little weird at the bottom. The decimal number 42 becomes 2a in hexadecimal. Wait, 2a? Let's break down exactly how that happens. To convert 42 into base 16, one way to do it is with division. We just ask ourselves, how many times does 16 go into 42? Well, it goes in 2 times, and there's a remainder of 10. That gives us our 2 digits, 2 and 10. But hold on. In hexadecimal, a single position can't hold the number 10, so the system has this really clever solution. And here is that solution. To represent the values from 10 all the way to 15 as single characters, hexadecimal simply uses the letters A through F. So that remainder of 10 from our last step becomes the letter A. This gives us our final hexadecimal number, 2A. You've probably seen this system all over the place, like in web design, where a color like pure white is just written as #FFF.
Now let's try this in reverse. How do we read a hexadecimal number like C2? Well, first we translate the C back to its decimal value, which we now know is 12. Then, just like with binary, we use place values. The C is in the 16's place, and the 2 is in the 1's place. So we calculate 12 times 16, and then add 2, which gives us a grand total of 194.
Okay, we've learned some pretty powerful translation skills today. But before we wrap this up, it's really important to understand the scope of these simple methods we've been using, just as the source material points out. Now, this is important to remember. The method we've been using is designed to be really simple and intuitive, which makes it a fantastic starting point. But the source material is clear that this is just one of many ways to do these conversions, and it works best for smaller numbers. So think of it as the perfect first tool in your new toolkit. So, the crucial point here is this. You've cracked the code. You've learned the fundamental grammar that underpins our entire digital reality. You now have a real tool to look at a string of ones and zeros and actually see the number hiding behind it. And that brings us to our final question. We've translated the language of numbers. But what about the languages of logic, like Python or JavaScript, or the languages that run the entire internet, like TCP/IP? What other digital languages are out there, quietly shaping the world all around us?